Join us today as we dive into the Internet of Things for autonomous vehicles. More specifically, the software that enables sensors and processors to talk to one another and to talk with external infrastructure. We'll be talking about the current state of technology when it comes to the IoT, the role of data distribution services in an autonomous vehicle, data-centric versus message-centric communications, and connecting a vehicle to the Internet of Things. Today's October 8th, 2019, and Bob Leigh of Real-Time Innovations, or just RTI, joins me. Bob's RTI Senior Market Development Director, and he's based in Sunnyvale, California. And who wouldn't want to be? RTI produces Object Management Group Data Distribution Services. We're going to find out exactly what that is. And that's for IoT applications. You know, IoT isn't new. John Romke put a toaster on the internet in 1990, and that was the first connected device. But according to Cisco, the Internet of Things was born between 2008 and 2009, when more things or objects were connected to the internet than people. We're glad you're back with us for this conversation. Welcome to Thinking Through Autonomy, a podcast to help you understand the promise and impact of autonomous land and air vehicles in our world. I'm Ken Dunlap, managing partner of Catalyst Go, taking you on this journey. Hear and read more at thinkingthroughautonomy.com. Now it's time to take your hands off the wheel, foot off the pedal, hand off that throttle, and let's go. Bob, welcome to Thinking Through Autonomy. It's great to have you on today.
Oh, great. Thank you. I'm happy to be here.
So I've been looking at your background, and you're somebody that I kind of characterize as part serial entrepreneur, part IoT evangelist, part IoT architecture strategist, and then a part developer of using IoT for green energy. And I'm just kind of wondering, can you share what that special thing is about IoT that makes you want to launch companies, devote your career to IoT, and then take those skills over to the autonomous vehicle realm?
Sure. I think you're probably being too generous there, but I'm happy to talk about that. I think the interest for me is in applications that are first challenging and new in that they're changing the way either business is done or the way, ultimately, I guess, the way society works, but also that they're having a direct impact. And I think the things that we don't really see so much when we talk about IoT in the consumer space, wearables and things like that, that's all, interesting, and maybe changing the way people live their lives in some ways. But when we look at the industrial side, that's changing the way whole industries are working and making them more efficient, or completely changing the types of services that we're doing, or even how society interacts and functions. That's the really interesting stuff, and so being part of that is really exciting.
I want to talk a little bit about your timing for a minute. You started two companies. You co-founded ProLucid Technologies in 2008, and that later spun off a subsidiary called Local Grid Technologies back in 2012. And your timing seems to be really right on. I mean, if you consider the fact that Cisco said that really the Internet of Things really didn't start until 2008, 2009, when we wound up having more connected things than we did have people on the internet. Yet your timing just hit it out of the ballpark. What was telling you back in 2008, if you put your Wayback Machine on, hey, this is going to be something that I really need to get involved in because there are great opportunities out here?
Well, I think the honest answer is just luck. That my personal path coincided with how IoT evolved, but it also just has to do with the type of work and industries I've been working in beforehand. Prior to Perlucid, I was working in what really is a direct IoT application in oil and gas before IoT became a common term and phrase, and that was just an opportunity that presented itself. Applying satellite internet technology to embedded technology, and the cost point got to the right time to apply it to this industry. And from there, I just wanted to keep doing similar things in working in technology, especially embedded technology, but connectivity and the internet and the importance of data was really important to the industries working in, including automotive. So it's just the right time to connect all those things together.
One of the things that I saw in your background is that you were really at the cutting edge of connecting IoT, I guess play on words, connecting IoT devices into the green energy revolution. What did you see in terms of green energy that IoT could be of additive value and make these systems even more efficient?
Well, I'd say that maybe that was even the bleeding edge, perhaps in hindsight. But I think the challenge with green energy is we're talking about ultimately a lot of smaller systems in a highly distributed network. And that's essentially what IoT is. So even if you just look at a conceptual basis, that you've got different devices all with information, how much can I produce, how much am I producing, how much can I store, just what is happening within the grid, that are in a truly distributed network located, in your neighborhood, down the street at a community center, where all these solar, wind, storage, whatever the device is, or whatever the green energy application is, are located everywhere. That really is IoT. And the only way to effectively deploy and manage these systems is to have a architecture where you can manage all this data and frankly manage it in real time, because the systems are so dynamic. So I think that just inherently it's required in that type of application.
Now, when I think about green energy, I'm obviously thinking about windmills, solar, but you mentioned that there's a wealth of data available. Where's that data coming from on these green energy platforms? What are you looking at?
Well, basically, if you're just talking about solar as an example, you're talking about how much energy is being produced. What's the capacity for the amount of energy that could be produced? Like, is the sun shining? How bright is it shining? And what's the capacity of the grid at that location to take on that energy? And, if you've got too much production in a certain area, you can overload some of the infrastructure. So you can't overproduce energy for any given region, whether it's a very local region or whether it's the entire grid. So that kind of data is essentially, and it applies to every kind of green energy asset. And the difference between green energy production and various distributed energy production and the traditional sort of centralized generation is, you don't have one place where you can get most of your information. You don't have a nuclear power plant where you can say, I'm going to measure everything at this nuclear power plant, and that's most of the information I need to manage my grid. Well, instead of one plant, I'm replacing that with thousands of different solar, you know, electric cars, storage devices, and wind generation that I then need to manage. So there's a lot more data per watt that you're producing that you need to aggregate, you need to manage, and you need to use to effectively run the grid.
If we just step back a moment and you reflect back on where the Internet of Things was as opposed to where it is today, where do you think we are? And are we doing enough things right, or are we doing things wrong? Where does this thing called IoT stand in terms of the technological development that we are leveraging and what we could leverage out of the IoT?
So I guess the challenge with IoT is, what's the benefit? Ultimately, how does it either make money or save money? Because it has to be driven by some sort of business needs. And I think the exciting thing about IoT is we're honing in on um, those applications that are actually valuable, as opposed to the early days when it was, let's try a bunch of different things and see how they work, and we're not really sure what's going to be valuable, and we have a whole lot of theories. I think really early on in IoT that I was involved, we were solving some very practical applications and weren't really calling it IoT. It was like, how do I get this data that's at a remote location, and how do I get it back to some server where people can actually use it? And once IoT took off and became a household name, there were just so many theoretical applications that we thought we could apply IoT to, and lots of government funded project and private funded projects, and many of them didn't go anywhere. And I think we're past that sort of hype cycle, and now we're focused on things that are truly valuable, which makes it a lot more interesting, I think.
Moving a little bit more into the present day and connecting IoT with what you're doing right now. You're at this company called RTI, which in many circles is a household name. And that company has its roots in Stanford, and you have a portfolio spanning aerospace to healthcare to energy to everything in between. And your software is on NASA rovers, it's on UAS system, ADAS, and driverless cars. Am I missing anything there?
Medical robotics,
Okay.
imaging systems. Yeah, there's a few oddballs thrown in there too. So
Yeah. Well, all of these things involve something called Object Management Group Data Distribution Services. That is not something I use in my daily life. I know that the industry lingo is DDS. Can you tell us a little bit about DDS?
sure. So DDS, as you said, stands for Data Distribution Service. It is a standard or a family of standards actually managed by the OMG, the Object Management Group. They're probably most famous for the UML standard, but DDS is something that our company has been working on for many, many years. It actually came from a technology we had called NDDS that was turned into this standard through cooperation with the U.S. Navy and other parties. And the idea is to create a communication standard and communication framework that's used between mostly embedded devices that can be used in a distributed manner and provides very reliable, robust, real-time communication. And it's originally used in the Navy, U.S. Navy. Every naval surface warship uses DDS and has expanded from there into many, many different commercial applications. So it's used in all these different applications where you have mission and safety critical requirements where you have data you need to share with other applications in the network in the system, and you need to make sure that it's reliable and it gets there in a very short order. Usually we were talking about physical systems, so it has to respond in physics time. So if you're driving a car, you need to be able to share information around different applications within that car so they can make decisions before you run into something. So that can be in the order of milliseconds or even microseconds.
One of the things, Bob, I was reading about is that RTI focuses on something called data centric DDS versus message centric DDS. And I don't know if that's a discussion of cats versus dogs in this business, but what do I need to be thinking about when I put my arms around a data centric messaging system?
So DDS is a data-centric framework. The idea is that the data is the important thing in your application, and I'm going to share data with other applications. And you were very familiar actually with another data-centric technology. That's a database. So a database is a data-centric technology. Every application that's part of some common system will interface with the database to share data with other applications. The difference between a data-centric DDS, or what we call a data bus, and a database is that a database is for historic data, something that's already been produced. I want to find out, what happened last Tuesday and, how many error messages I had in my system on that day. Whereas a data bus, which DDS is an implementation of, is looking forward in time. It's like, I want to look, I'll use the autonomous vehicle example. I want to look for all objects moving towards me at greater than 5 meters per second within a 50-meter radius. And so then a data bus will get you all that information and provide that information to your application in real time, but it's all forward looking. Now this is different than message centric, where message centric architectures, which is what most machine to machine or computer to computer communication is about taking data, packaging it into a message, and then sending that message to another application, and that application then unpacks that message and gets the data that was sent to it. So the data is really contained within this message. You don't, when you send that message out, you don't know what the data is. You don't know anything about the data. You can't do queries and filters on that data. You're basically sending messages off blindly as a communication framework, like we are sending message off blindly, and then the application has to deal with it at the other end. Now, data centric, because the data is first class citizen within the infrastructure, then you can do things like filtering, you can do things like queries, like I mentioned, and you can have a more direct connection to the data and different sources of data within the network.
You mentioned the data bus. Again, that's something that I don't work with on a daily basis, but a data bus essentially to me sounds like it's that backbone infrastructure where you can take a series of distributed systems, whether they're sensors, whether they're um, auxiliary processors, and you feed that back into the main CPU. That's a simplified version of a data bus. But um, help me understand just a little bit more about the data bus and really its importance in a system like an autonomous car.
So the data bus, first thing to understand, it's all software, it's all a logical construct. It doesn't have any physical embodiment, but it is very similar conceptually to what most embedded developers would be familiar to hardware data bus, things like CAN bus in a car or the backplane on your computer. But it's all logical, and it is what you mentioned, where you're making data available to, from sensors to all these different CPUs, but we're doing it in a very intelligent way, so that your application sees this data as local memory. It's accessing data as local memory. It's saying, I need all sensor information provided to me. I'm going to need, the speed of the car. I'm going to need the location to the car, and I need all this information within my application. Now, the data bus as infrastructure takes care of all the details. So it's going to go out and find out, where does the sensor information come from? Who are the sensors connected to the network? I'm going to get data from them. Where do I get speed from? I know that's coming from, some sensor on the wheel. So I'm going to get that information. I'm going to make sure it's all available to your application. So it's very simple for the application, but the infrastructure itself is very complex. So this is a very powerful tool in that the application developer doesn't have to worry about where the data comes from, how many sources of data there is. It's only working with this data bus directly, and that looks like local memory. The trade-off of this is that we have to be very clear and specify what's the format of my data, my system, what's the organization of the data, something we call it, like what we call a data model, how we're going to define the different data, and I'm going to need to know in advance all the data that your particular application is going to need, so I can provide it to you at the right time.
Now, did you just describe something called Connect 6, one of RTI's flagship software services?
Well, Connect 6 is the latest version of our Connect DDS product, and it's the implementation of DDS data bus. So if you hear the term data bus or DDS, that's the DDS is the standard. Data bus is a generic term for a DDS or a data centric like technology, and Connect 6 is our product that's an implementation of that.
Let's transition over to one of my favorite topics, autonomous vehicles. And we kind of touched on that earlier as we were speaking. Sometimes I struggle to understand how data is flowing inside an autonomous vehicle. At a high level, I understand, well, we need to know the speed of the car. We need to know what the LiDAR is doing for us. We need to know what the optical systems are telling us, or even the radar system. Can you kind of just maybe draw an outline of that data flow inside, particularly and specifically an autonomous vehicle? And really, what are the challenges that poses?
Yeah, I can certainly try to do that. There's lots of different approaches to the architecture at when you get down to details, but generally the approach is the same. You want to sense what's around in the environment. You want to process that information, or what they call think, and then you want to act on that information, and that's a loop. But when you break that down, there's lots of different levels of sense. So you've got lots of sensors providing information, and these are independent sensors that are providing data that's not coupled to each other in any way. The best you might have is time synchronization, and probably not good enough to actually rely on it. But you're going to have data coming from your camera, you're going to have data coming from a LiDAR sensor, you're going to have data coming from your radar, you're going to know the speed, you're going to know the location of your car. So you're going to have a first level of of processing on each of those senders just to identify objects, for example. Figure out what's in my image frame. Can I identify, that there's a bike, that there's a car, that there's a person? And then your LiDAR system is going to have some sort of similar process where you have all this information collected from a LiDAR sensor, and you need to identify what are the objects within that sensor. Then you're going to have another level of processing where you need to match up, and this is called sensor fusion, match up objects that you detect in LiDAR with objects you detect in radar, with objects you detect in the image frames from the camera. And so then we can maybe put together an accurate view of the environment that's around the car. And then you have multiple other levels of processing where you need to figure out what is everything doing, is which direction is the person walking, how fast is the car driving, in the lane in front of me, in the lane beside me, what are their likely paths that they're going to take, what are my paths, what options do I have to avoid collisions, if I'm going to go forward, if I'm going to turn right, if I need to avoid an object, should I go to the right, should I go to the left? And all of this is being continuously computed within the vehicle. This is part of the sense and then think. And then you also have to layer on, okay, what do I want to do? Am I driving forward? Am I taking the next exit? Do I need to turn right? And then within the path that I want to take, what are my options? So there, you can see that there's many layers of processing here that need to account for the route you're going to take, the contingencies you need, and what everybody else is doing in the environment. And then there has to be a step where you actually go and execute that. And that's not necessarily simple either, because you're talking about a machine that needs to drive smoothly turning right. So that's a fairly difficult control problem in this chaotic environment with less than perfect information. And that doesn't even begin to talk about some of the other aspects of autonomous vehicles, connectivity to the cloud and getting data from some back-end servers, accurate maps and things like that, or some of the newer systems that actually monitor the person that's in the car to see if they're paying attention, to see if their hands are on the wheel, if it's, not a fully autonomous system. So there's a huge amount of complexity in terms of the processing and the data available. And this data has to flow from, as you can imagine, from the sensor to applications that do the first level of processing, to the next layer of processing, to the thinking algorithm, to the acting algorithm, and then just monitoring algorithms. So you've got a huge amount of complexity all in this one, small package that you need to deal with, and it's all about the data.
Let's kind of do a thought experiment here for a minute. So let's say you and I start Honest Ken and Honest Bob's autonomous vehicle car manufacturing company. And we want to challenge the likes of the big six that are out there doing autonomous vehicles right now. As we sit down and start scoping out the major decisions we have to make, sitting right here, it occurs to me that the data distribution model, the data distribution bus needs to be like the first thing we think about. Or am I approaching that wrong? That, this is just another software application and we can catch up with that later.
No, you're absolutely right. It is actually an architecture decision. So it's usually one of the first decisions made by an architecture team, by an engineering team, long before they even start development on the application. So we are involved, years before a product reaches market. Some cases 6 to 8 years before a product reaches market, because we're involved right at the early research stage where they're trying to figure out how are we going to architect this system, what's the framework, what's the platform we're going to build on, long before they choose even the hardware that is going to be running on.
Have you signed so many NDAs that you can't tell us about the customers that you have that rely on your architecture?
Yeah, that's absolutely true. Maybe the
Okay.
most challenging part of my job is I can't tell you anything about the customers or who I'm working with, because they consider it part of their IP and technology strategy, the fact that they're using DDS, and they don't really want to talk about it until they launch their product. Now, we are going to be at CES this year, and we will have 2 or 3 customer success stories, we call them, or use cases talking about customers, if not announced before then, by CES. So that'll be pretty exciting for us.
I can't wait to go see that. I didn't know you were going to be there.
Yes.
You gonna be working the booth?
Yep, yep.
Ah,
We've
okay, all right. So
got a booth in the Westgate, so happy to
okay,
book some time to
I
meet with you there.
I hope we get the chance to meet. I just want to maybe just go through a couple more nuances here because this is incredibly fascinating. So if I am the developer of a driverless vehicle, we've made our decisions on architecture, but the technology keeps moving around us, and eventually there are going to be different sensors, different processors, different components that we might think need to be put in this vehicle. How flexible is this data architecture we're talking about? I mean, if suddenly you're dealing with COTS parts 1 minute, and the next minute you're dealing with one of these highly proprietary black boxes that no one will tell you about how it works, how do you ensure going down the road that you continue to have interoperability?
So that's one of the great things about ConnexDDS and a data-centric architecture is your interface between applications is all about the data. It means it's very decoupled from what the actual application is on the other end. So what you're doing when you're building a data-centric system, and I mentioned it was an architecture choice, is you're defining the architecture system around the data that needs to be shared. And typically when you're getting information from a commercial off-the-shelf sensor, or you build a custom sensor, or you have something that's wildly different, you're still trying to get the same data. The data may be a little different, it may have do different features, but fundamentally the data is going to be the same. So you're normalizing that information, regardless of who it's coming from, to a standard format that everybody agrees on and everybody interacts with. So what you really can do, and this is one of the reasons that we are selected and used in autonomous vehicles, is delay those decisions or even make changes to the decision about what hardware, what modules, even what applications are interfacing to your system, down the road till you have to make the decision. It's not something you have to commit to up front.
One of the things that I've noticed is that there seems to be a line drawn between level 3 and level 4 cars. So level 1 to 3 cars are in one group, level 4 and 5 are another, when you start talking about data distribution challenges. And I'm kind of wondering, why is there that line between level 3 and level 4? Is that the amount of data you have, or is it something else I'm not thinking about?
So I think the line is actually shifting. You're right, but I think the line is actually shifting, and we're seeing that level 3 may be just as hard as level 4, even though on paper it may not look that way. And I think it depends on the OEM approach. But really the difference between the first group and the second group is how much, for us anyway, how much data do you need to manage? And that is another way of saying how complex is the software and the system you're trying to build. So when you're talking about a level 4 autonomous vehicle, that vehicle needs to be in control. The system needs to be in control with no driver at all times under certain conditions. So that means the driver does not need to pay attention, and the driver will not need to take over control. So that level 4 system needs to deal with most of the contingency cases, most of the use cases that it's going to run into, including all the rare and exceptional use cases that don't happen 98% of the time. That's really hard to do, to get everything that, or just about everything that the car needs to deal with, compared to level 2 and some of the maybe easier level 3 functionality where the driver is available. In level 2, the driver is still responsible. The driver still has his hands on the wheel. When we get to level 3, the driver needs to be available and with comfortable transition times. And that's sort of the difficult part, is what does comfortable mean? But essentially there's a driver there to back up the car, so if it runs into a situation it doesn't know how to deal with, the driver can take over. So this is the big difference: data and complexity of software to be able to deal with all these extra exceptional situations that we may get into.
And I'd also think, though, that there are a number of automobile manufacturers that are kind of using level 3 as the testing platform before they go to level 4 and flip the switch and turn on all the capabilities that these systems have. So, maybe the data is needed at that level 3. It's just that you might not be able to buy the level 4 um, applications of that right
Right.
now.
And actually, what we're seeing is it's starting even earlier, especially with the traditional OEMs. They're just adding more and more features to level two until it becomes almost a level three. And that you're absolutely right. That is the proving ground to get to level four in the future. So they really need architectures that will support level four much earlier than they actually sell and implement level four.
If we switch gears a little bit here, Bob, metaphorically, let's talk about data security because I'd have to think that that winds up being one of the number one priorities when you think about data management in these vehicles. What are you kind of seeing in terms of trends on data security? What are you concerned about when someone calls you up and says, "Hey Bob, we've made an architecture decision. We want your application to be the backbone of this vehicle we're building. Tell us what you do on security."
Yeah, security is definitely important, and I think we're seeing a big change in the approach and need for security. Whereas historically, and essentially until a few years ago, industrial systems were secure because you couldn't access them. They weren't connected wirelessly, they were behind brick walls, so your security was really the fence around whatever cyber physical system that you had. Um, Autonomous vehicles kind of demonstrate to the extreme how that is different, but it's not just about autonomous vehicles. It's really all industrial cyber physical systems that are connected to a network now. But with an autonomous vehicle, you have multiple wireless access points, as well as the ability to physically access a car. And so that creates a huge security vulnerability and challenge. At the same time, you also have a control system within the car that needs to run. It needs to fail operational. If you have a security breach, you can't just say, oh, shut the network down and we're going to stop working. It still has to run so you can apply the brake and drive to the side and stop the car. So how do you deal with that kind of security? For us, it's a different approach. There's a standard called DDS security that's part of our product, but it is a standard that allows you to apply security to the data and do what we call fine-grained security, where you can apply security policies, different security policies to different types of data depending on what the system requires. So you can imagine that a car's location might be something you want to encrypt because you don't want someone to come and, you know, connect to your car wirelessly or be snooping on the 5G signal and figure out where your car is because it can get the GPS location. But something like the temperature of the engine or the temperature of the bearings in a car, doesn't really matter that people know that information. There's no need to encrypt it, but you certainly want to be sure that you know where that information is coming from, that you authenticate the source of that information so that you can rely on it for your control algorithm. And this is the kind of fine-grained security you can get with DDS, which first of all reduces the amount of processing power you need to manage the security and do encryption because you apply it selectively, but also creates a more robust system in that you can build system where you authenticate what's necessary. You can have reliable communication without encryption, and you can encrypt where you need to. And this can be a very powerful tool for these industrial remote applications.
If we extend this conversation back to those off the shelf parts that we were touching on earlier, if you're a vehicle manufacturer and you've invested in this kind of architecture and you know that the architecture has good security behind it, but you buy something from Honest Ken's car parts or Honest Ken's LiDAR parts and you connect it to your vehicle, how do you need to think about securing an off the shelf component into a highly engineered and refined, maybe proprietary system? Because we know that manufacturers are going to do that because they can't make everything.
Right. Yeah, and that's another reason that the automotive industry is a bit of an extreme in this security requirement. You have hundreds of suppliers, hundreds and hundreds of suppliers supplying components into a vehicle. So when you talk about security, first thing, you need to trust your supply chain. You need to know that the CPUs you're buying and the chips and the silicone that are going into your car are from a trusted source, that they're not compromised, when they're manufactured, or when the operating system is built, or at any point along the supply chain. So that's probably the first thing you need to look at. But we're talking about hundreds and hundreds of components. It's not going to be perfect. So the other way, not alternative, but in addition, that you should approach this is, how can I be sure that the components in my car are only going to do what they're supposed to do? And this is where fine-grained security can also help, in that you can assign permissions to applications and devices that are required for them to operate and do their function, but no more. So we've seen some of the hacks in taking over remotely of a car, usually done through the infotainment system, either a wireless gateway, or the dashboard, and it's supposed to be isolated from the main control bus, the CAN bus of the car, but it isn't. So by bridging from an external network into an internal network, they're able to take over the car. Well, if you had fine-grained security policies, then you would be able to say, well, this is an infotainment system. It shouldn't be able to write to anything. It can only, read data that it needs to display, and it can't write to any data on the bus. Well, then if you had this compromise of the infotainment system, you still wouldn't be able to access the data on the internal network. And this can really help in isolating different applications and providing more robust security. And it's really not even about compromises alone. It's also about, is there a bug? Is there a problem with the software? Does it do something that it's not supposed to? And we can isolate these commercial off-the-shelf components so that they're only doing, and they only can do, what they're supposed to.
In the last couple minutes we have left, Bob, what I'd really like to do is understand, I guess, the problems, the processes, challenges, the advantages of the systems that we need to connect our autonomous vehicles to, if it's either the urban infrastructure or the infrastructure of the vehicle manufacturer for over-the-air software upgrades. I'd like to understand how this car now becomes just another device on the IoT that needs to connect someplace else and do it safely and securely.
That is a challenging question to answer, because
That's why
yeah.
it's one of the last ones.
Yeah, well, there's multiple trends going on, and really, to get an answer to that, you're trying to guess, how do these things converge. So we know that the car is becoming more autonomous, more intelligent, and it's kind of on its own track to reach higher levels of autonomy, driven by competition, driven by safety, driven by, perhaps regulations down the road, that encourage the OEMs to invest and develop this technology. But that trajectory is entirely independent of things like 5G, and smart cities, and other, like, vehicle to vehicle or vehicle infrastructure technology. It's sort of a technology with value on its own. Then we have cities investing in smart city technology, where they want to better manage traffic and share data with cars and get data from cars. We have the B2B and B2I standards emerging, where cars are going to share information with each other and share information with, roadside sensors about, what's going on, where they are, who they are. And if we look into the future, at some point, all of these technologies will mature. I want to guess which ones come first, or how fast they come, or anything like that. But if we, look a decade or more into the future, we're going to have all of these things. And now we have a car that's part of a wider transportation network and infrastructure, where you have information about traffic in real time. You have, lights connected to that track of information, that are perhaps communicating directly with the cars that are stopped at the light. So the light itself knows which direction the cars want to go, and can optimize, when it's green and when it's red. Or if you imagine fully autonomous cars, we don't even need lights. We just have information shared between the cars, and then negotiate who goes first, who goes next, and they completely optimize the intersection. And then we perhaps even go further, where we've got cars commuting with people on their cell phones. So you can detect a person is about to come around a blind corner, and And if they're not paying attention, you're not going to run them over with your car because the algorithm was aware of that person before it could even see them. So we have this whole network of information driven on all on data, and a lot of data all connected together in this future. And I can't even imagine what the applications are going to be, but certainly at the core is more efficiency and better traffic and something that's safer. But I'm sure we'll have many more applications that we come up with once we've actually got this technology in place.
Well, Bob, you have the last word on thinking through autonomy. I want to thank you very much for this conversation, and I really enjoyed the discussion.
All right, thank you, Ken. I really enjoyed it as well. Thanks.